Okay, today we are going on to chapter 3, uh, vectors. And so if you want to follow along, the book I am doing this out of is Physics for Scientists and Engineers with Modern Physics by Surway and Jewett. So Surway is known to be a pretty good textbook. So yeah, let's get into it. All right, so 3.1 goes over coordinate systems. Now, to just preface this a little bit, right? So why do we need to learn about vectors? Well, they're very useful and they're used a lot, right? Um, Vectors, which, let's see here, are used in many different applications, right? You're going to use them in every part of your education, really, going forward. If you're an engineer or in some STEM related courses or fields, right? So the book says it is imperative that you master the techniques discussed in this chapter. Now, hopefully, you will take this not lightly, right? I did, right? And well, that'll bite you in the butt if you don't. So yeah, just um, make sure to really soak in these ideas, right? Like vectors to me seem really scary at first, and I just didn't give them the respect they deserved, and they definitely deserve a lot of respect because they're really useful tools for in physics, especially, right? But they're used everywhere, and so yeah, I just wanted to say that. So don't be scared of them. They're your friend. So yeah, let's start with 3.1, which is coordinate systems, right? So I'm just going to read along the chapter. So many aspects of physics involve a description of a location in space. In chapter 2, for example, we saw that the mathematical description of an object's motion requires a method for describing the object's position at various times. And we went over that in the last video. In two dimensions, this description is accomplished with the use of the Cartesian coordinate system, in which perpendicular axes intersect at a point defined as the origin. And so, yeah, a Cartesian coordinate system. So that's really simple. It's just a oh, Cartesian coordinate. Now, you'll also have all these other little lines, right? And so what you would do is you would label this as the origin, right? And then this is the x-axis. This is the y-axis, right? And so if we were just do a very simple coordinate system, so if you put a spot here, we have the coordinate to 0, right? So the dot particle is located at 0y 2x, right? So that's a Cartesian coordinate system. And so Cartesian coordinates of a point in space representing the x and y value of the point and expressed as x, y are also called rectangular coordinates. I believe this is done so because, well, it kind of looks like a rectangle. I think that's true. I'm not really sure. Sometimes it is more convenient to represent a point in a plane by its plane polar coordinates. So the plane polar coordinates are this, where r is the radius and theta is the angle in respect to the x-axis, right? And so in this polar coordinate system, r is the distance from the origin to the point having Cartesian coordinates x, y. Oh, yes. Sorry. Yes. I say the radius because if we drew a circle like this, or this would be the radius, right? But that's not necessarily what we're talking about, sort of. But so if we had a dot out here, right, this r is this length, right? And theta is the angle between a fixed axis and a line drawn from the origin to the point. And so that would be this angle right here. The fixed axis is often the positive x-axis, and theta is usually measured counterclockwise from it, right? Yeah, so anytime you're going to measure an angle, you were going to measure it from this way, right? So if we start here at y equals 0, right? And let's say, yeah, and so you're going to measure this counterclockwise, right? You're going to go from there to there. So like if we were to have a circle, right, and you wanted to measure this, you would measure it counterclockwise, right? And so from the right triangle in figure 3.2b, okay, we find that sine theta equals y over r and that cosine theta equals x over r. Yeah, and it talks about review of trigonometric functions is given in the appendix B4, right? So trigonometry is a prerequisite to physics, which is a to physics, yeah, and also a prerequisite to calculus, which is a prerequisite to this, right? So, yeah. So once you get into physics, they're hoping that you know trig pretty well, because it's a tool used in physics quite often. And so yeah, let's draw this right triangle, right? Maybe let's draw a little bit better, right? And they label this theta x, y, and r. So think of this as the triangle that we had here, right? So here's our x, right? And we measure theta counterclockwise from x. So of course that's going to be our theta, right? This is our distance to the point x, y, right? Yes. And so they say, okay. Oh, well, yeah. And so first they drew this right here, right? And they say, okay, y, x, right? And so this is the coordinate xy, right? And so if you were to draw a line right here, it would be this exact triangle, right? And so they give us some trig identities. So sine theta equals y over r, right? Yes. R cosine theta equals x over r, and tan theta, for the tangent, theta equals y over x, right? So another way to look at these in a more trigonometric way would be this is the hypotenuse, this is the opposite, and this is the adjacent, right? So these are all correlated to where they are in reference to theta. Right. So the hypotenuse is always the longest side. The opposite side is opposite to the angle theta. In x, the x side is adjacent to your angle theta. And so a good way to remember these is SOHCAHTOA. So sine is your opposite over the hypotenuse, right? So that's y over r, right? Ca, which is cosine, is adjacent over your hypotenuse. And we see that's correct here. Tangent, TOA, is opposite over adjacent, y over x. And so it's a really easy way to remember these. Uh, I know I had a problem memorizing them, but anyways. And so, what do they say? Okay, so conversely, if we know, okay, so okay, and so what they're saying from this, okay, so they're saying also we can find the values of x or y with these equations right here. And conversely, if you know the let's say you know x and you know theta, well then you can find r, right? And if you know y and you know theta, you can find r. Or if you know y and r, you can find theta. You need to know two things though. You need to know. I believe that's true, right? Now you can do a system of equations, but we won't go into it. So conversely, if we know the Cartesian coordinates, the definitions of trigonometry tells us that the polar coordinates are given by, they label this tangent theta equals y over x, and then r equals x squared plus y squared. Yeah, the square root of x squared plus y squared. And so yeah, that's another way to find r. These four expressions relating the coordinates x, y to the coordinates r theta apply only when theta is defined as shown in figure 3.2a. In other words, when positive theta is an angle measured counterclockwise from the positive axis. These apply only when theta is defined as shown in figure 3.2a. Okay. When positive theta is an angle measured. Okay. Some scientific calculators perform conversions between Cartesian and polar coordinates based on these standard conversions. Yeah, so another friend of yours is your calculator, right? So if you find the time, definitely look at your calculator and see if it can make these conversions between Cartesian and polar coordinates. That could help you out, especially if professor giving you the test allows you to bring in a calculator that can do this, right? Let's see. If the reference axis for the polar angle theta is chosen to be one other than the positive x-axis, or if the sense of increasing theta is chosen differently, the expressions relating the two sets of coordinates will be different from those above. What do you? Listen, if the reference axis for the polar angle theta is chosen to be one other than the positive x-axis, or if the sense of increasing theta is chosen different. Oh, yeah. So yeah, if you start here from y instead of x, yeah, saying it needs to be right? Is that what it's saying? It's saying that the angle needs to be from the x-axis. If not, then chosen differently. Expression relating the two sets of coordinates will be different. Yeah, yeah. Okay, well, yeah. So just make sure that you're keeping the x-axis as your reference axis, right? If not, then changes everything. And so let's see here, example 3.1. So in order to do 3.1, let's erase this. We'll keep this up here for reference. We'll keep those up. So example 3.1. Oof. The Cartesian coordinates of a point in the xy plane are xy equals, okay, so the coordinates xy negative 3.50, 0, and negative 2.50 meters. As shown in figure 3.3, find the polar coordinates of this point. So let's go ahead and erase this. Okay, so we have, okay. So negative 3.5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, well, let's go ahead. 1, 2, 3, 4, 5. Label your axes and yeah, labeling. You can just make sure to always label. It's just your professor is going to love you and you're going to love yourself later on. So let's see here, negative 3.50. So this is the x, this is the y, right? So negative 3.5. So it's going to be in between 3 and negative 3 and 5. So 1, 2, 3, or negative 3 and 4. 3 and 4. So right there. Okay, I just like to make a dot for each coordinate and then bring them in the middle. So negative 2.50, 1, 2, 3. So it's going to be in between 2 and 3. And then that's your coordinate. Boom. So this is your x, that's your y, and this is xy, right? And that's your spot, right? So polar coordinates, right? So we should be able to do this, right? So let's think about it. Okay. So in order to find a polar, okay, so we know that x equals r cosine theta, y equals r sine theta, right? Yes. Okay. Okay. But we just have x and y. We don't have the angle either, right? But that's our angle. This is a theta, right? So we can find r because this is x squared plus y squared, right? So we know r. So so x squared negative 3.5 squared plus negative 2.50 squared, all under that. Let me grab my calculator. All right, so what do we get here? Square root of negative 3.50 squared plus negative 2.50 squared. Okay. Yeah, you got to make sure and put your parentheses around the numbers just like that, right? Okay, so what do we get? Well, we get equal to the square root of 74 over 2, which is equivalent to 4.301. Right, I like to at least go to 3 significant digits, just because, well, aren't we all trying to go to the moon? And apparently they went to the moon on 3 significant digits, which is wild, right? Okay, so 4.3. So R equals 4.301, right? Okay, so now, so we have our R's and we have our X's. So now we can find theta, right? So, okay, so let's see, what is the, okay, so X equals R cosine theta, right? So we want to divide both sides by R. So those cancel out. We get X over R equals cosine theta. So then theta equals the cosine inverse of X. Is that right? I think that's right. Yeah. Okay. So you find the inverse cosine. Should be a little button. Should be a little button on your calculator, sort of like that. And then X over R. So our X is a negative 3.5, and it's crucial that you put the negative 3.5 in there over R, which is 4.301. All right. Okay, so it says it's equal to 144. Well, let's go ahead and put the 0.465 degrees. So basically 144.5 degrees, 5 degrees, which is basically 145 degrees, right? And so we know that, huh, hmm, interesting. Hmm. Yeah, what I'm confused on, so this is basically 0. This is 180 degrees right here, right? So really 145 should be right in there somewhere. Hmm. Let's see what we get when we do this one. So y equals, so basically do the same thing. Yeah, you basically do the same thing. You get the theta equals the sine inverse of what, y over r. Let's see what happens there. So y is negative 2.5 over r, which is 4.301, which is negative 35. Huh. 0.539 degrees, right? So, oh, hmm, okay. So, the book says we need to find, we actually use our tangent. Hmm. Okay. Huh. Okay. All right. Well, we messed up there. That's fine. We're here to learn, right? Okay. So we've got that. Okay. Huh. I guess that makes sense, right? Hmm. I don't know. Anyways, let's. Okay. So tangent theta equals y over x. So in order to get this, we do the inverse of y over x, which equals, the inverse, tangent inverse of y over x, which equals negative 3.5 over negative 2.5. And of course, putting in the negatives doesn't really matter here since they're going to cancel out because of positive, which equals 54. What is going on? Hmm. They're getting 216. 360 minus 54. No. We must use the sine of x and y to find the point lies in the third quadrant. That is theta equals 216, not 35.5, whose tangent is also 0.7. So answer to both r and theta. Okay. Yeah. Yeah. So this is 270 degrees, right? So we know it's supposed to be in between there. So they do this, right? They get, y over x, negative, wait a second, did I? Oh, 35. Oh, plus 180. Oh, okay. Here we go. So, yeah. So if you do it the way that I did it before, right? Tangent inverse y over x. This equals 35 point. What was that? 35.5 degrees, right? So that is this right here. So which is on this line. So all we have to do is add 180 degrees and we get this right here, right? So we do 180 plus 35.5, we get 215.5, which is roughly 216 degrees, which is the answer. So, interesting. Okay, so, I wish I had a good answer for why we don't get, like, why do we have to add 180, right? Hmm. Maybe let's ask ChatGPT, right? That's why we have my computer here, is so that we can ask ChatGPT. Here we go. Let's take a. Actually, I'll take a picture with. No, no, never mind. Picture. Actually, I'll take a picture with. No, no, never mind. Picture. Camera. So take a picture here. Yeah, because I don't really get why we would have to add 180. Why don't we just get that answer? So I wish I would have left the answer what we had before. Hmm. Hmm. It says, "Oh yes, the infamous add 180 trick." Da, da, da. So the arctangent function doesn't know what quadrant you're in. It's just blindly spits out an angle between -90 and 90. -90 and 90. Okay. Or negative pi over 2 or pi over 2, which is the right half of the coordinate plane. Yes. So why do we add 180 sometimes? Because arctangent can't tell the sign of a of x and a y together. It only sees their ratio. When to add 180 or okay. Okay. Let me look at something really quick. Huh. Okay. Okay. This is good. Okay. So it says, let's go ahead. Erase this. Okay. So it says, okay, if you're in the quadrants, right? So this is quadrant 1, this is quadrant 2, this is quadrant 3, this is quadrant 4, right? So when you're in quadrant 1, let's do this. So quadrant AX, AY. Nah, that's not the answer. 216 is the answer, though. 216 is the answer. Even if we did that. Oh, da, 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 da. Where did that go? Oh, Okay, this is weird. Okay, maybe we'll move on from this. I'm trying to think of why even ChatGPT is giving us a hard time here. Um, So what happens if we do this? Whoa, that's not right. Hmm. Okay. Yeah, it has something to do with the signs, right? Okay, so this is the chart it gives me. So we're in Q1, Q2, Q3, Q4, right? So we have plus plus, minus plus, minus minus, and plus minus, right? So these are your signs here, right? So if you're in quadrant one, then you just give the answer. You just give the answer from what you get here, right? If it's a negative and a positive, you subtract 180 degrees. If you're in quadrant three and both your signs are negative, you add 180 degrees. And if you're in quadrant four and your signs are plus minus, you subtract 360 degrees. I guess. Huh. Okay. So just let's see what it says in the book. So it says, notice that you must use signs of x and y to find that the point lies in the third quadrant of the coordinate system. That is theta equals 216, not 35.5, whose tangent is also 0.714. Answer to both r and theta agree with our expectations in the conceptualized step. Yeah. Okay. Yeah. So this is what you have to keep in mind. You have to keep in mind, you have to think about, okay, what quadrant are we in? We know we're in quadrant three, right? So if we get a value that's in quadrant one, we just add 180 because quadrant three is 180 degrees from quadrant one, right? So I hope that answers the question, and I hope I didn't confuse you guys here. But this is exactly how I wanted it to go, honestly. I knew we were going to come across some issues and sort of my understanding. This is why I'm doing this. Because I want to grasp these things more, right? I'm the president of Physics Society. I should know physics more. I should understand it more. Even though vectors isn't really physics, of course, but we use it all the time in physics, right? Just in my research that I'm doing now, which is in material science, which is very physics heavy. It's all about physics, right? Um, we're using vectors to try to understand, well, really matrices, which is a what sort of vectors can add up to be, right? And so yeah, these are things that I need to know, and we all should know if we're sort of going down this path, right? But let's move on. Vector and scalar quantities 3.2. All right, so let's erase. Let's erase. Oh yeah, I'm be honest. I wish I could have gone through that a little bit smoother, but it's okay. All right. 3.2, vector and scalar quantities. All right. So we now formally describe the difference between scalar quantities and vector quantities. Yes. When you want to know the temperature outside so that you will know how to dress, the only information you need is a number in the unit degrees C or degree F, right? So Fahrenheit or Celsius. Temperature is therefore an example of a scalar quantity. A scalar quantity is completely specified by a single value with an appropriate unit and has no direction, right? So yeah, it's not a vector anymore. It is just a discrete number. Other examples of scalar quantities are volume, mass, speed, time, and time intervals. Some scalars are always positive, such as mass and speed, right? You can't go at negative speed, right? You can just go very, very slow or not at all. Others, such as temperature, can have either positive or negative values. For me, I hope we're never in the negatives. Those are the scary temperatures to me. I hate the cold. But anyways, the rules of ordinary arithmetic are used to manipulate scalar quantities. If you are preparing to pilot a small plane and need to know the wind velocity, you must know both the speed of the wind and its direction. Because direction is important for its complete specification, velocity is a vector quantity. Yes. Yeah, okay. And so it gives a definition of a vector quantity is completely specified by a number with an appropriate unit, the magnitude of the vector plus a direction, right? So yeah. Um, yeah. So another example of a vector quantity is displacement. As you know from chapter 2, suppose a particle moves from some point A to some point B along a straight path as shown in figure 3.4. We represent this displacement by drawing an arrow from A to B. Yeah. Suppose a particle moves from some point to some point. Yeah. So we have a particle here, and it went here, right? So okay, yeah. So let's say for some reason this is the path that the particle took, right? But how we would represent that is just with a straight arrow. And so that is the total displacement, and this is the complete path. Okay. We represent this displacement by drawing an arrow with the tip of the arrow pointing away from the starting point. Yeah, so this is the starting point, ending point. And so the arrow is in the direction of the ending point. If a particle travels along some other path from A to B, such as shown by the broken line, figure 3.4, the broken line, its displacement is still the arrow drawn from A to B. Displacement depends only on the initial and final positions. So the displacement vector is independent of the path taken by the particle between these 2 points. Keep that in mind. In this text, we use a bold-faced letter with an arrow over the letter, such as, to represent a vector. Oh, actually, they do it this way. It's what we normally do, or what I do anyways. That is a representation of a vector. Another common notation for vectors with which you should be familiar is a simple bold-faced character. But typically, we don't use these because, well, this is just easier. And There's a bunch of other reasons why you wouldn't use it. Um, yeah, but this is just the easiest way to draw a vector and to know that you drew a vector, right? Another common notation, yep. The magnitude of the vector A is written as either A or A. Yes, so they sort of write it in italices, which I don't ever see anybody using. Or you can write it uh, magnitude, right? So this is the vector, and this is the magnitude of of that that vector. The magnitude of a vector has physical units, such as meters for displacement or meters per second for velocity. The magnitude of a vector is always a positive number. What about the vector to follow in our opening storyline? And it asks, what heading did your friend give you to Catalina Island? You can use a latitude and longitude finder online. Okay, well, we'll skip that. Okay, so here's some questions it asks. Which of the following are vector quantities and which are scalar quantities? So your age. So think about it. Your age is just a discrete number, right? Say for instance I'm 5. Yeah. So that's a scalar, right? Acceleration. Ooh, acceleration. I wouldn't say that's a vector. Yeah, that's a vector. So acceleration is a vector, right? Because you can accelerate in some direction, right? I think. Let's see. I'm pretty sure. Let's ask ChatGPT. So let's see. Yes, because it has a magnitude and a direction, right? Yeah. So let's think about what is acceleration. So a equals dv over dt, right? And this can change, right? It can you can the velocity can sort of, yes, it can change. It can change. It's variable, right? Whereas your age is not variable. You are 5, right? Um, yeah. Velocity. Velocity. Well, yeah. Velocity is dx over dt. So I would assume maybe we can make this assumption, right? Is any derivative, anything that's made up of a derivative, right? Um, is a vector, right? I'm pretty sure. I wonder. Let's see here. Speed. Speed. Your speed. You're going 55 miles an hour in some direction, right? Speed seems to be, yeah. Speed seems to be a vector as well, right? Yep, velocity is a vector. Scalar. No direction. Car doing donuts at constant speed has changing velocity because no direction changes but constant speed. Only has magnitude, no direction. Oh, but acceleration. Hmm. Okay. So velocity is a vector. Speed is not. Speed is a scalar. So it gives an example of 30 meters per second. No idea where it's headed, it says. It's the magnitude of velocity. Oh, okay, yeah. If you think about it like that, speed is if you say speed equals the magnitude of the velocity, and this is just going to be some discrete number, right? And yeah, that makes sense. And of course, yeah, the next one is mass. And yeah, that's definitely a scalar, right? Something is 5 pounds, right? It doesn't change um, depending on its direction or, um, yeah, it has no direction, right? Yeah. Okay. Let's see. What else are we going to do here? Do we keep going? Yeah, let's keep going. All right. Basic vector arithmetic. Okay. So, yeah. Okay. So it says, oh, okay. Let's go to 3.3. So yeah, that section is basically over vectors versus scalars, right? So hopefully we have a good idea of what vectors uh, and scalars are, right? And how we can tell what the difference is. So 3.3 basic vector arithmetic. Whoop, whoop. Okay, so yeah, this is alluding to us being able to arithmetically manipulate or do arithmetic. How would you say that? Do arithmetic with vectors, right? Two vectors A and B may be defined to be equal if they have the same magnitude, if they point in the same direction, right? So let's just draw two equal. So, well, imagine. Okay, so we're going to label this one A, B, and don't forget your arrows, right? These are the same, they're in the same direction, in the same magnitude. So we would say A equals B. Da, 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 da. And so it's saying we can also add two vectors together, right? So yeah, so it's saying we can add these two together, right? And so you would say boom, boom. So is that a scalar then, or what? What? Or is that just one? Okay. Yeah, R equals A plus B. So here's a better way to visualize it. So if you have A and you have B, so this is A, this is B, right? And your resultant vector, which is the The resultant vector is the resulting vector you get when you perform some um, arithmetic on it, right? So let's say we add these two together. Well, then our resultant vector, R, is this, right? And so whenever adding, they talk about adding tip to tail, right? So here's, right? Isn't that what they say? Oh, yeah. So whenever you add these from the tail of A, the tip of B, and that's where you draw your resultant vector to, right? Okay, and you can add more than just two, right? Let's let's do the same thing, right? But then let's have C going this way. Now, breaking these up, you could just say, okay, well, this is A, and then B, and then C, right? But then when you add them together, it equals this one. And so the resultant vector, well, let's do it right. Would be that right there. Oh, head to tail method. This technique for adding vectors is often called head to tail method. Okay, head to tail method. All right. Does that make sense? Head to tail. Head. Okay, yeah, adding this head to that tail, this head to that tail. Right, that makes sense. Notice that adding the vectors a plus b equals c is very different from just scalar addition. So yeah, so this is not the same as a plus b plus c. The first equation is a vector sum, which must be handled carefully, such as with the graphical method. The second equation is simple algebraic addition of numbers that is handled with the normal rules of arithmetic. Okay, so when two vectors are added, the sum is independent of the order of the addition. This fact may seem trivial, but as you will see in chapter 11, the order is important when vectors are multiplied. Procedures for multiplying vectors are discussed in chapter 7 and 11. This property, which can be seen from the geometric construction in figure 3.8. Okay, yep, okay, okay. So 3.8. So, blah, 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 blah. That doesn't look right. Oh, yeah, it's really hard to draw. But am I doing that right? Yeah. Oh, of course. Yeah. So this, okay, so A, B, and then this is B, this is A, right? You want them to be perpendicular to each other, right? So then our resultant vector is that right there. Right, and so they say, okay, so they say R equals, oh, R equals A plus B equals B plus A, right? Yeah, which we can see. A plus B and B plus A are the same thing. Yeah. When three or more vectors are added, their sum is independent of the way in which the individual vectors are grouped together. A geometric proof of this rule for three vectors is given in figure 3.9, where two ways of adding the same three vectors are shown. This property is called the associative law of addition. Yeah, so the associative law of addition, which is A plus B plus C equals A plus C. We have described adding displacement vectors in this section because these types of vectors are easy to visualize. We can also add other types of vectors, such as velocity, force, and electric field vectors, which we will do in later chapters. When two or more vectors are added together, they must all have the same units, and they must all be the same type of quantity. Yeah, okay. It should be meaningless to add a velocity vector to a displacement vector because these vectors represent different physical quantities. Makes sense. Yeah. Yeah, you can't add meters to speed, right? Anyways, the same rule also applies to scalars. For example, it would be meaningless to add time intervals to temperatures. Yeah, yeah, makes sense. To just visualize this, right? Like, um, let's say you have, I don't know, let's say 5 meters and 5 degrees Celsius, right? You're not going to add those together. You can't add those together. You can only add like things, right? So you can only add 5 meters plus 5 meters, or 5 degrees Celsius plus 5 degrees Celsius, right? The operation of vector subtraction makes use of the definition of the negative of a vector. The negative of the vector A is defined as the vector that when added to A gives 0 for the vector sum. So that is, okay, yeah, so let's just erase this. So A plus negative A equals 0, right? So if we were to, let's say this is A, and then negative A, we're right back at the place we were, right? So we started here, and we end up here. So that equals 0 when we add them together. The vectors A and negative A have the same magnitude, but point in opposite directions. We define the operations A minus B as vector negative B added to vector A. Okay, yes. So, yeah. So A minus B is actually A plus negative B. The geometric construction for subtracting two vectors in this way is illustrated in figure 3.10a. Okay. We would draw B here if we were adding it to A. So A minus B Hmm. Hmm. Okay. So yeah, this is what it's showing. It's Let's give it black for a little bit. Okay. So okay. So we have A. And we have negative B. Right. And I'm guessing negative B because we're sort of pointing in the other direction, right? If this were a positive, I think we'd have an arrow there. Yeah. But it's a negative, so we're sort of pointing in the opposite direction of A, right? So A minus B is this. Yeah, yeah. A minus B. Yes, we're just um, connecting those, and then yeah, and then it shows positive B right here. So, like I said, it would be in the opposite direction, or it's same direction as A, right? It's still sort of working in. So you can always think of your Cartesian coordinates, right? So everything over here is positive, and everything over here is negative, right? So it's pointing in A is pointing in a positive direction. B is sort of pointing in a negative direction. But this positive B is pointing in this sort of the same positive direction A is, right? Okay, so scalar multiplication of vectors is straightforward. If vector A is multiplied by a positive scalar quantity m, the product m times A is a vector that has the same direction as A and magnitude ma. Okay, so so you have A, and you want to multiply it by m. Well, this equals um, ma. So if you have, let's say A, let's say m equals 2, right? So this is A. Then A m. Well, let's do a little bit better than that. Let's do this, and it's 2 times longer, but in the same direction, right? So that's scalar multiplication. If vector A is multiplied by a negative scalar quantity, negative m, the product negative ma is directed opposite A. Okay. Okay. Yeah. Um, okay. Yeah. So it just sort of puts it in the opposite direction, huh? Yeah. Okay. So let's say m equals -1. Then yeah, I think you get what I'm doing. Yeah, it's just pointing in the opposite direction, right? For example, the vector 5a is 5 times as long as a. Makes sense, right? Because it's here, multiplied it by 2, it's 2 times as long as a. And points in the same direction. The vector -1/3 times the vector a is 1/3 the length of a and points in the direction opposite of positive vector a. Makes sense, right? The magnitudes of two vectors a. Okay, so these are sort of quick quizzes at the end of this section here. The magnitude of two vectors A and B are A equals 12 units and B equals 8 units. Which pair of number represent the largest and smallest possible values of the magnitude of the resultant vector R equals A plus B? Is it 14.4 units, 14.4 and 4 units, or 12 and 8 units, 20 and 4 units, or none of these answers? The magnitudes of two vectors, A and B, are A equals 12 units and B equals 8 units. Which pair of numbers represents the largest and smallest possible values for the magnitude of the resultant vector? Well, wait, what? 12 and 8. Isn't not going to be B? Isn't that going to be 12 and 8? Which pair of numbers represent the largest and smallest possible values for the magnitude of the resultant vector? Hmm. Hmm. Well, we don't know what direction they're pointing in. 12 and 8 is 20. I want to say 12 and 8. I don't. We can ask ChatGPT. I don't really get what they're asking here. Let's go to the next one. So quick quiz 3.3. If vector B is added to vector A, which two of the following choices must be true for the resultant vector to be equal to 0? Okay. So this one, let's write it down. Okay. If vector B, so vector B added to vector A, which two of the following choices must be true for the resultant vector to be equal to 0? Right? So you want this to equal 0. You want R equal to 0. So either that's negative, and that's positive, but A must be equal to B, but negative, right? So A and B are parallel and in the same direction. No, because if they're parallel in the same direction, adding them together would give you that. So that wouldn't not equal to 0. B, A and B are parallel in the opposite direction. That's it. Okay, so because we saw this earlier, right? Those two are equal, opposite direction. This is basically equal to negative A, right? Next choice is A and B have the same magnitude. No, but they need to be opposite. A and B are perpendicular. No, it's gotta be B. B. Yeah. A and B are parallel and in opposite directions. That's the answer. We're almost done with this chapter. Yeah, almost done. A car travels 20 kilometers due north. Let's see. I'm gonna get a drink. 1 second here. Anjali. Okay. So example 3.2. Let's see here. Let's use green. A car travels 20 kilometers due north. Okay. So, yeah, so let's label this one A. So, 20 kilometers. Um, yeah. And then 35 kilometers in a direction 60 degrees west and north, as shown in figure 3.11. Okay. Okay. Yeah, so it's sort of mapping this to a, okay. Let's just draw the coordinate system here. X. Actually, they're in directions, right? So north, south, east, west. All right. And then so the first one goes, we're going to say this A. Let's just put A over here. 20 kilometers north, right? And then so B sort of goes 60 degrees. Try to do this as well as I can. Let's go ahead. Let's label this 60 degrees. 60 degrees right there. Um, and it goes 35 kilometers. Yeah, so it's a little bit long. Yeah. So B, 35 kilometers. We're going to say northwest, 60 degrees from north, right? 60 degrees from north. So, find the magnitude and direction of the car's resultant displacement, right? So the resultant is this right here. This is R. So R equals A plus B, right? Right? So we know, yeah. Okay. What's kind of crazy is they just sort of throw this at you. And they didn't really. Hmm. Right? They don't really even. They show you how to do the problem, right? In the problem. But they don't really. They didn't really give you these equations, though, right? They didn't. Hmm. Hmm. Okay. Hmm. Hmm. Okay. So let's go ahead and draw this other one that they drew. So they labeled this. Hmm. So they labeled this theta. They label this beta, right? And then they come over here and they draw another one. where the resultant vector, do it in the same color. Oh, where's my green? Oh. Right. So they draw this. Right? And then this resultant. So this is R, A, B. Right? Right. Okay, and then they label this still beta. Okay. Okay. Yeah, so this is essentially this right here. Then, yeah, and then, yeah, okay. Kind of like a parallelogram, right? So, yeah, if you put those together, you get this, right? And this is your beta, and that means this is beta, right? These angles are the same, and these angles are the same. Okay. I don't know. Okay, so they say for the graphical method for finding the resultant displacement vector r equals a plus b, adding the vectors in reverse order b plus a gives the same result for r. Okay, cool. I don't know why exactly they do that, but I wish they would give you a reason. They don't. So it says in the conceptualize, the two vectors a and b that appear in figure 3.11a, so this is the first one, help us conceptualize the problem. The resultant vector r has also been drawn. We expect its magnitude to be a few tens of kilometers. The angle beta that the resultant vector makes with the y-axis is expected to be less than 60 degrees. The angle that vector b makes with the y-axis. Okay. It says categorize. We can categorize this example as a simple analysis problem in vector addition. The displacement r is resultant when the two individual displacements a and b are added. We can further categorize it as a problem about the analysis of triangles. So we appeal to our expertise in geometry and trigonometry. Oh, okay. I guess we're supposed to be experts in trig. Yeah. Makes sense, right? It's a prerequisite. So analyze. In this example, we show two ways to analyze the problem of finding the resultant of two vectors. The first way is to solve the problem geometrically using graph paper and a protractor to measure the magnitude of r in its direction in figure 3.11a. In fact, even when you know you are going to be carrying out a calculation, you should sketch the vectors to check the precision. Try using these tools on R, the resultant, in figure 3.11a and compare it to the trigonometric analysis below. The second way to solve the problem is to analyze it using algebra and trigonometry. Okay, the magnitude of r can be obtained from the law of cosines as applied to the triangle in figure 3.11a, see appendix B4. Okay, law of cosines. Yeah, law of cosines. So let's go to the appendix B4. Let's do what we're supposed to do, right? Oh, B form. Oh. Okay. Okay. So it says the law of cosines. Okay. Okay. So the law of cosines is this. So first maybe we should put this alpha plus beta plus gamma equals 180 degrees. So a squared plus, oh no, sorry. A squared equals b squared plus c squared minus 2b cosine alpha. B squared equals a squared plus c squared minus 2ac. Oh, did I? Oh, BC. BC. AC cosine beta. C squared equals a squared b squared minus 2ab cosine gamma. Okay, this is gamma. Okay. Yeah, it's got a bunch of other trigonometric identities back here. Really useful. Okay. Maybe let's put a little. What's that? What page is that? I wish it had a page number. Anyways. Okay. Ah, yes. So, so So R is our C, right? And we have A and B, right? Okay, so then R equals R squared equals A squared plus B squared minus 2AB cosine gamma. And then, yeah, so then we take the square root. Gamma, right? Now it's just plug and play, basically. Except for, what is our gamma? Because it, yeah. Okay, so our gamma is this. Yeah, which this is 180. Right? Am I doing that right? 180 minus 60. So, yeah. Oh no, that'd be 60 plus 90. That's 150. Yeah. Yeah. Nope, this isn't right. A gamma. So they say it's 180 minus 60. So let's go 180 minus 60. 140. 120 degrees. One hundred and 80 minus 60. Why are we am I missing something? It's the gamma value, and gamma is right. Isn't that what they gamma, not beta? Alpha. This are gamma. This are alpha. Hmm. Wondering. Okay, so this angle is this angle. Ah, so this, yeah, I think I was right. I don't know. Let's ask ChatGPT really quick. I just want to be sure. I'm not 100% sure. 180 minus 60. That angle is that angle, I think. I think this is 60 degrees right here. Pretty sure. Pretty sure. It's gotta be. Yeah, it's gotta be. So yeah, I think it's looking at this triangle right here. Hmm. Okay. Let's see if ChatGPT can give us an answer. 2289 61. Okay. Let's take a picture. 120. I mean, that makes sense, right? But this is 120 degrees minus 60. That makes sense. What I don't understand is why we're using this one instead of this one. Okay, but it looks like I mean, look, it says use 3.11a. Oh, now we're kicking it with colors. Oh, did I not upload the? Oh, snap. Oh, my bad. You gotta upload the problem to get a right answer, right? Hmm. Mm. Oh, or is it this theta? This is the theta. Which, which, that looks 120 degrees, right? How do we? So that's. How do we find that? We find that from this. Okay, so the law of cosines, once the angle between vectors placed tail to tail. You mean head to tail? The angle between the two vectors. Okay. Yeah. So the law of cosines, it wants apparently the law of cosines wants the angle in between the two vectors. So it's this angle right here. Right. So that's good to know. Right. But then how do we find that? Right. So hmm, how do we find that? Hmm. Right now that I've know the answer, it's hard to really think about. Two known sides of triangle. Tail to tail. Shit. Tail to tail. What are you talking about, dude? Two vectors. Hmm. Once this is the theta. Angle between two vectors is the angle inside the triangle when placed tail to tail. Tail to tail. Yeah, I guess we just subtract this from 180. That's hmm, hmm. Okay. So let's move on. Maybe I'm thinking about it way too hard. Okay, 20 points. So A equals 20 squared plus B is 35 minus 2 times 20 times 35 times cosine. Really, this should be theta, which equals 120 degrees. Right, so that equals 20 squared, 400 plus 35 squared minus, let's do it, 2 times 20 times 35 times cosine 120. Yep, 48.22 to, what is it, meters? Oh, kilometers. Right, okay, and then it says use the law of sines to find the direction of r. The direction of r. Okay, so it says use sine beta over b equals sine theta over r. Let's go back to the book, in the back of the book, and see if that matches. Okay, so in the back of the book, the equation is this: a over sine alpha equals b over sine b beta equals c sine gamma, right? So, okay. So, guessing. So why can we? Well, it's fine to flip it, right? The flipping is not what's bothering me, right? So essentially, what we're doing is, so remember our c equals r in our equation. So really, this is r, right? And so we can just flip these, which I'm not really sure why they're flipping them. Let's do it without flipping, right? Um, my question is, why can't we just leave that alone? Why can't we just leave that alone? Huh. Anyways, so B sine beta equals R sine gamma. They use theta. Okay. Okay. Ba, 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 ba. Okay, and so yeah, I mean, it doesn't. We can flip these, and it doesn't do anything to the problem, right? Other than just some simple math manipulation. And then we're wanting to get sine beta on one side by itself. That's probably why they did it, because it's easier to divide out when you have sine. If you want to get sine by itself, it's easier whenever it's on it's the numerator, right? So so sine beta equals b over r times sine theta. Okay, and then so our b, we know our b is 35. Our r 48.22, sine of 120 degrees, right? And so we're looking for, yeah, we're looking for beta. So we could take the sine inverse. Yeah. So beta equals the sine inverse of all this, right? Yeah. So let's see what that gives us on the calculator. So sine inverse of 35 over 0.22, the sine 120, which, by the way, you should know what sine 120 is, but it's fine. Okay, boom. Okay, boom. I get 38.9. So our beta equals 38.9, which is what the book gets. And so that's what beta is. That's what beta is. And so that's the resultant. So, okay. Okay. So it says, so the resultant displacement of the car is, so we can sort of write that down here. Yeah, sorry, I write sort of in cursive and non cursive. Car is 48.2 kilometers. In a direction of 38.9 degrees. 38.9 degrees. And so that's the answer. Yeah. Yeah. So if the car is driving 20 kilometers north and then decides to go take a turn 70 degrees to the west and head 35 kilometers, then the total displacement is 48.2 kilometers, which is this R, in a direction of 38.9 degrees, which is this beta. Boom. So that's the answer there. All right. Dun, 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 dun. Okay. Wow. This is getting to be pretty long. I think we're gonna stop there. I don't. Hmm. Nope. We got this. We got this. We got this. Okay. So components of a vector and unit vectors. Um, so we'll ask us some questions really quick. Let's see here. Does the angle beta that we calculated agree with an estimate made by looking at figure 3.11a or with an actual angle measured from the diagram using the graphical method? Well, we didn't do the graphical method. I don't have graph paper, so let's just see what I said. Although the head to tail method of adding vectors works well, it suffers from two disadvantages. First, some people find using the laws of cosines and sines to be awkward. Okay. Second, a triangle only result. Second, a triangle only. A triangle only results if you are adding two vectors. If you are adding three or more vectors, the resulting geometric shape is usually not a triangle. Yeah. Yeah, we saw that with adding a plus b plus c earlier. It was a weird rectangular shape. In section 3.4, we explore a new method of adding vectors that will address both of these disadvantages. Okay. So it says, what if? Suppose the trip were taken with two vectors in reverse order. 35 kilometers at 60 degrees west of north first, and then 20 kilometers due north. How would the magnitude and direction of the resultant vector change? Taken with two vectors in reverse order. And then due north. It says they would not change. The commutative law for vector addition tells us that the order of vectors in an addition is irrelevant. Graphically, 3.11b shows that the vectors added in reverse order give us the same resultant vector. Yeah, that makes sense. Yeah, if we just did the things in opposite order, it doesn't matter, right? If we did A first and then we did B, we would get the same resultant as if we did B first and then A. So that's all that's trying to say. Okay, so 3.4. I'll be honest, this vectors chapter is not the most exciting, right? But um, you just need to have some discipline and just get through it, um, right? It seems sort of arbitrary. You've got these lines, right? And you're adding these lines together, and you're just like, well, so what? But you'll see later. It's really is one of the most or one of the best tools you'll have in your tool chest. Anyway, so 3.4 components of a vector in unit vectors. Okay, so it says the graphical method of adding vectors is not recommended whenever high accuracy is required or in three-dimensional problems. In this section, we describe a method of adding vectors that makes use of the projections of vectors along coordinate axes. These projections are called the components of the vector or its rectangular components. Any vector can be completely described by its components. Consider a vector A lying in the xy plane and making an arbitrary angle with the positive x-axis as shown in figure 3.11 1 to A. Okay, so we have right. Always make sure on label. Okay, so we have this, right? But it's saying that it's made up of your AX and AY, right? So you have your vector in your X direction, you have your vector in your Y direction, right? And that, and if you add these together, you get your resultant vector here, which is they're labeling just your A. Right, okay, and then of course we have some angle theta, and they just sort of trying to show that it's just one big rectangle, I guess. This vector can be expressed as the sum of two other component vectors, ax and ay. We see that three vectors form a right triangle, and that a equals ax plus ay, right? So a equals ax plus ay. We shall often refer to the components of a vector a written as ax, a sub x, a sub y, without the boldface notation. The figure 3.2b shows it's slightly different. Yeah. So 3.2b shows the same thing, but just in a different way. Right? Okay. So we have our, but now, right? Well, yeah, it's a square. Anyways, and so this is the same as this, right? Or supposed to be. And so, yeah, what they're sort of saying is you can sort of, origin, of course, you can sort of write the same thing in two different ways here, right? And so we see that the components a sub x represents the projection of a along the x-axis, and the component a sub y represents the projection of a along the y-axis. These components can be positive or negative. The component a sub x sub for subscript, the component a sub x is positive if the component vector a sub x points in the positive x direction, and is negative if a sub x points in the negative x direction. Right? Yeah. So if it's pointing this way, so that's a positive. If it were to be pointing this this way, then it'd be a negative a sub x, right? And the same for y, right? This would be a negative a sub y, right? The coordinate a sub x is okay. A similar statement is made for the coordinate y. From figure 3.12, in the definition of sine and cosine, we see that cosine theta equals a sub x over a, and that sine of theta equals a sub y over a. Hence, the components are okay. So we can write this. So cosine, right? Cosine theta. Oh, x over a and sine theta. All right. Now I don't know why they don't have the, but they don't have these on there. Okay. And then so they say that a sub x equals a cosine theta a sine theta. Right? You're gonna want to memorize these, right? Or I hesitate to say memorize, because you should just be able to sort of derive them if you have to. But if you just work with them a lot, you will remember them, right? So just work through these problems as much as you can and try to memorize these. Anyways, the magnitudes of these components are the lengths of the two sides of a right triangle with a hypotenuse of length A. Therefore, the magnitude and direction of A are related to its components through the expressions. Yes, so the magnitude of A, magnitude, magnitude of A, which is really represented this way, is what x, yes, ax squared plus a y squared, and then equals a x over a y over a, yeah, a y over a x, where, yeah, theta equals the tangent inverse of ax. Okay. Notice that the signs of the components a sub x and a sub y depend on the angle theta. For example, if theta equals 120 degrees, a sub x is negative and a sub y is positive. Yeah. Yeah. So remember, we are can think of this as the different quadrants, right? Quadrant 1, 2, 3, 4, right? So if we're in, let's say, quadrant 2, right? Well, x is negative and y is positive. From quadrant 3, right? They're both negative, negative, negative. For here, they're both positive. So, um, yep. And then this one is just the opposite of that one, right? Bada boom. When solving problems in two dimensions, you can specify a vector A either when its components a sub x and a sub y, or with its magnitude and direction a and theta. Yeah, 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 yeah. They say the same thing, right? So, just like this, you can represent this, or a vector A, by its resultant and its angle, or by its two components, right? In many applications, it is convenient to express the components in a coordinate system having axes that are not horizontal and vertical, but are still perpendicular to each other. For example, when we will consider the motion of objects sliding down inclined planes. For these examples, it is often convenient to orient the x-axis parallel to the plane and the y-axis perpendicular to the plane. Yeah, so like this. Let's say you have a, yeah, let's say this is a slide, right? We have a we have yeah, and then we have a kid walking up it, right? So what you'll typically do is you'll call this the x axis, and you'll call this the y axis. Which, and you may already know, but we also call this the normal line, which is the line perpendicular to the surface we are analyzing. All right. So it's a quick quiz 3.4. Choose the correct response to make the sentence true. A component of a vector is always okay. A component of a vector is always larger than the magnitude of a vector. A component of a vector is never larger than the magnitude of the vector, or a component of a vector is sometimes larger than the magnitude of the vector. A component of a vector. So we have a vector, right? Vector A, and the components AY or AX is always larger than the magnitude of the vector. No. Sometimes, yeah. So yeah, sometimes the component, right? Yeah. What if you have this? The resultant is just this, right? Yeah. So sometimes, right? Sometimes larger than the magnitude of the vector. Yeah. So, okay, moving on. Vector quantities often are expressed in terms of unit vectors. A unit vector is a dimensionless vector having a magnitude of exactly 1. Now, I'll be honest with you, this tripped me up all the time, but you'll get used to it. So the unit vector, vector having a magnitude of exactly 1. Unit vectors are used to specify a given direction and have no other physical significance. They are used solely as bookkeeping convenience in describing a direction in space. We shall use the symbols I, j, and k to represent unit vectors pointing in positive x, y, and z directions. So, yeah. And hopefully you are taking notes along with me. It's probably the best way to go about this. I don't know, maybe listening one time through, taking notes the second time through, or I don't know, whatever works for you, I guess. So you have x, y, z, right? Which x, y, z, right? Well, you can also represent them with these letters, I, j, and k. And to denote that they are unit vectors, put a little hat on top of them. Da, da, da. Yes, and these are pointing in the positive directions, right? So let's say this is 1, 1, 1. So 0, 0, k would be that right there. 1, 0, 0 would be that right there. 0, 1, 0 would just be that line right there. So this is 0, 0, 1. This is 1, 0, 0. And this is 0, 1, 0. Dun, 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 dun. The hats or circumflexes on the symbols are standard notation for unit vectors. The unit vectors I, j, and k form a set of mutually perpendicular vectors in a right-handed coordinate system as shown in figure 3.1 or 3.14a, which, yeah, I've already drawn here. The magnitude of each unit vector equals 1. Okay, yeah. So basically my phone died. So yeah. Okay. So but I know where we're at. So consider a vector A lying in the xy plane as shown in figure 3.14b. The product of the component A sub x and the unit vector I is the component vector A sub x equals A sub xi, which lies on the x-axis, and the magnitude, yes. Okay, so yes. Got a new pin too. That was nice. Well, not new pin, but yeah, these whiteboard markers are really nice. You just reload them instead of having to throw them away. And I don't know. I just got super conscious of like throwing big pieces of plastic away constantly. So, and I saw Leonard Susskind using them. I was like, let me get those. Right? He's a famous physicist, and so yeah. I don't know. Anyways. Okay, so yeah, let's draw this right here. So we have this resultant. This vector, right, which can be represented by your x and a. Really, this should be on the line. Anyways, and a y, right? So this resultant vector, or just vector, um, can be represented by two separate vectors, right? So with x and y. So this vector here has an x and a y component, where if you had, let's put it down, if you had this, so x, y, oh, well, z, y, and let's say you have this, right? Which here it's sort of hard to tell exactly where that's pointing, but and let's just call this A, right? Well, you would have to represent this, or it could be represented by AX, AY, and AZ. So three different components, since it's three dimensions, right? So it says consider a vector. Oh, been there. Okay, so then therefore the unit vector notation for the vector A is yes. So essentially what this is, like what we saw earlier, is that this is the basically the addition of these two components, right? So A equals AX plus AY, right? Oh, and then so we can also represent this like this. So I hat and J hat, right? I forget if I went over this, but just a really quick recap, right? So I believe I did, but I, J, and K hat, right? So these are how you really how you represent the vectors, right? So this is actually X, Y, and Z. But for vector notation, this is how we represent each component of the vector, right? So this would be I, J, and K, right? So anyways, I believe I went over that. If not, yeah, it'll be all right. Anyways, consider now the polar coordinates shown for the point in figure 3.2, the point of the first quadrant in figure is reproduced in figure 3.15. So yeah, so it says that essentially, okay, so yeah, we can do this. So we have some vector here, right? And so R, and then this is angle theta, right? And so we can sort of represent it in polar coordinates as well. And so yeah, so this is a unit vectors for a point described by polar coordinates, right? Da, 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 da. Okay, now let us see how to use components to add vectors when the graphical method is not sufficiently accurate. Suppose we wish to add vector b to vector a in equation 3.12, where vector b has components bx and by. So b, let's so b has two components, bx, by. Now, I'm going to start to drop these subscripts x and y, right? It just takes forever, right? And you should know I means x, j means y, k is z, right? So, okay. Because of the bookkeeping convenience of the unit vectors, all we do is add the x and y components separately. The resultant vector r is okay. They okay. Okay, so it's saying we also have an a, right? So we also have a, which has a. After this, I'm done writing the subscript, right? Okay, and so the resultant vector, right, of r equals a plus b, right? This equals a plus b I plus a plus b j. Oh, yeah. But first, this is a x plus a y, right? Yeah, I j plus b x I plus b y j, right? And so we can then basically just factor out our a plus b's because whenever we go to add um, these components, you can only add I to I and J to J, right? You can't add I and J together. Only you can only add like things. Okay, and so because R equals okay, so because so because right R equals Ri plus Rj, we see that the components of the resultant vectors are so Rx equals ax plus bx, right? And Ry equals ay plus Vy. Therefore, we see that in the component method of adding vectors, we add all the exponents together, like what I just said a minute ago, to find the exponents of the resultant vector and use the same process for the y components. We can check this addition by components with a geometric construction as shown in 3.16, right? So we have this resultant vector, right? And this is made up of A and B, right? So A, B, we'll say this is the resultant, right? So then what we see from this is we can sort of break this down to visualize the components, right? So okay. Okay. So we see that this right here is our AX component, right? This is our AY component, right? This is our BX, right? This is our BY. This is our RY, right? And then RX is that. So sort of breaking it down component by component, right, for each vector, right? And so the magnitude of r and the angle it makes with the x-axis are attained from its components using the relationships. Yeah, so the magnitude of r equals rx squared plus ry squared, right? Um, which equals, if we sort of break this down a little bit further, ax plus bx squared plus ay plus by squared, right? Now think about also, think about what if we had a c component, right? Then you would easily just add this, well, you would have to, there'd be some cx and there'd be some cy, right? But anyways, just sort of trying to think ahead a bit. And so yeah, this is the magnitude, right? Magnitude or really the length of the resultant, right? It's really what that is. Okay. And this is, remember, this is a scalar, right? This is a scalar, right? Because it has no direction. We're going to find the direction. How do we find the direction? Well, we use our tangent theta equals y over x, right? Which is essentially our ay plus by over ax plus bx. Yes. Oh, and this would be your ry rx, right? And so at times we need to consider situations involving motion in three component directions, right? So we'll just right? Z, X, Y, right? I mean, most motion in the real world is happening in three directions, right? It has some X, Y, and Z component, right? So how do you represent that? Well, let's go ahead and erase this. So if you have a vector A that is three-dimensional, right? 3D, right? You have I plus J plus K, right? Or I wonder if they say, yeah, they say AX, X, A, Y, Z, right? So because, yes, because this is the resultant, right? This is resultant. So if you have some, right, and you have, this is A, right? So you have some X component, have some Z component, and maybe have some Y component, right? Yeah. And then of course your B is, BXI. I know I said I'm going to quit that, but it's really sort of, I don't know. Maybe I'm just by the book kind of guy. I don't know. YJ plus BZK. Right? Okay, and so the sum. So what is the sum, right? Well, we know this. We should be able to just spit this out. So A plus B equals A plus B I plus A plus B J plus A plus B K, right? And if you want to, Y Z Z. And maybe, you should be doing this in the beginning to just make sure it's ingrained into your head that X is I, Y is J, Z is K, right? Notice that equation 3.19, which is the equation we just looked at, differs from equation 3.13, which is basically, yeah, it's just the 2D version of this. So 3.13 is the 2D version of R, right? As a Z component, yes. If a vector R has X, Y, and Z components, the magnitude of the vector is, we talked about this, the magnitude equals A, or you can abstract this even further, right? And then, of course, each one of these has A, B, possibly C components. The angle theta sub x that R makes with the x-axis is found from the expression, yeah, so yeah, cosine theta x, Rx, or R, sine theta x equals Ry over R, right? With respect to the y and z axis, okay. The extension of our method, right? So then what is, I don't know. They don't tell us that. The extension of our method to adding more than two vectors is also straightforward using the component method. For example, a plus b plus c, we went over that, right? Okay, so for which, okay, so we're going to do two problems here. Well, we're going to do the quick quiz, and then we're going to do the example 3.3 out of the book. We plan to do some more problems for this chapter. This is getting to be a long video, so yeah, I think we'll just do maybe some problems at the end of this chapter in a different video or something like that. Or if you have any suggestions or what you guys want, I'm down for whatever. So for which of the following vectors is the magnitude of the vector equal to one of the components of the vector? So what does that mean, right? So which of the vectors is one of the components the same or equal to the magnitude, right? So basically it's saying that you have some vector and it has some components, right? So one of these components, say it's one of these components is equal to the magnitude. So yeah, which in here you wouldn't, right? Yeah. So okay, so the first one is what 2i plus 5j 2 squared plus 5 squared. So what? That's 25 plus 4. That's square. Wait, whoa, what? 25 plus 4. That's 29. Right? Yeah. Um. Yeah. That's what 5 times. Blah, 5 25. So it's like 5.4 or something like that. Anyways, so that's not it. So b equals negative 3j. Right. So the magnitude equals negative 3 squared equals 3. That's not it. It would have to be a negative. That would have to be a negative 3 in order to be the same as that component. So that's not it. That's not it. So we'll circle that. I'll just say 3. Oh, and then so C. Okay, so boom. Okay, so let's do this the correct way. So let's do the magnitude of C. So 0 squared plus 0 squared plus 5 squared equals square root of 25, which equals 5. Well, that's the same as that component. So C is the answer. C is the answer. All right. And then we will do example 3.3. Okay, I just like writing in the black pen. I don't know, it's nice. Okay, find the sum of two vectors a and b. Find the sum. So r equals a plus find r. Find r. right? Lying in the xy plane. So I'm guessing since we're going to find r, we're also going to find, it doesn't specify, it literally just says, find the sum of two vectors a and b lying in the xy plane. And yeah, and given by these two vectors, but I'm sort of seeing where it looks like they're wanting us to find also the angle, right? If we're going to find the resultant, we might as well find the direction it's pointing in, right? So 2 and 2, so A equals 2I plus 2J, right? And they always put these in parentheses. I'm not really sure why, but anyways, so 2 and 4, 2I plus 4J. So this is essentially plus a negative 4J. I like to do that just, yeah, because this is basically a vector, a negative direct vector pointing in the opposite direction, negative. Anyways, yeah, I just like to make sure that we know it's a negative vector, so pointing in the negative y direction. So we just add like things. Um, so yeah, let's just write this out, right? So we can do this. 2 plus 2I plus 2 plus negative 4J, right? So this is 4I hat plus 2 minus 4 is negative 2J hat, right? So R equals that, right? Okay, so might as well plot this thing. So 4I, right? 1, 2, 3, 4. 1, 2, right? So it's going to be that right there, right? And we might as well draw our other. So A is 2I, 2J, so up 2 over 2, right? And then over 2, down 4. 2, 1, 2, 3, 4. Right. So yeah, that looks like the resultant, right? If you were to this over here, put that right there. Yeah. So this is what this is A, B, A, B, and that's R. Right. Okay. So what's the angle? Well, what's that? Or really what we should be thinking about is this angle. Right? Okay. So we know we're in the Q4, right? So yeah. So whenever we go to do our type it into our calculator, we know it's probably going to be wrong. We may have to add 180, subtract 180. I don't know yet, but so let's figure it out. So the equation to find the angle is tangent theta, which is what, ry over rx, right? Which equals ay plus by over ax plus bx, right? Yeah. Anyways, okay. So then, which equals this equals negative. 2 over 4, so that's equal to negative 1/2. So if we do this the nice way, an easy way, tangent inverse of negative 1/2. So what does this equal? Negative 26. Yeah, yeah, which is this angle right here. This is negative 26 degrees, right? So how do we get this one? Well, we just add 360 degrees, which equals 333.44 degrees. And that's the answer. So that is the direction. This is the direction. And, oh, did we not? Oh, we didn't find the magnitude. Okay, so let's find the magnitude really quick. So the magnitude, let's put it over here. The magnitude of R, didn't we? No, equals 4 squared plus, they say negative 2 squared. That's going to pop out. So 16 plus 4, that's the square root of 20. So it's not 5, it's just 5, so about 4.5. Is it 4.5? I believe it's, yeah, it's 4.5. So that is the magnitude, equals 4.5. Bada boom. So those are answers. So yeah, that concludes this chapter. Like I said, if there's any problems you would like us to solve, yeah, just let us know. I'm down. And so next we'll be going on to chapter 4. Let's sort of look ahead really quick. Motion in 2 dimensions. That's why we need these vectors, right? Yeah, yeah. So we can look at motion in 2 vectors and solve them with vectors. Solve these problems with vectors. And so we're looking at circular motion, so probably maybe some centripetal force. Angular speed, yeah. Centripetal acceleration, all right. Oh, we're not into forces just yet. Relative velocity, relative acceleration, tangential and radial acceleration, some exciting stuff, interesting stuff. This is, you think about angular momentum and circular motion. I mean, think about the atoms. Atoms are doing this as we speak, right? They're really all about, and they're having some angular momentum and the angular forces. And thanks to those forces, we're here, all right? Like without those forces, without those, yeah, those things occurring, I wouldn't be here talking to you. My iPhone wouldn't be recording this. And our ability, our human ability to be able to represent these things with equations allows us to make things, engineer things like the phones, like these pens, like, everything you see around in this material science lab. Yeah, I mean, um, yeah, magnetism has is um, magnetism arises because of the angular momentum, the what they call the spins of atoms, right, and electrons. Um, yeah. And then chapter 5, we get into the laws of motion and Newton's laws, first, second, and third laws, which really should be the most exciting exciting thing to you at this moment? I mean, we're diving into physics, and finally, we got past some of the more boring things, especially like vectors. Vectors are really dry and abstract, but I'm telling you, they're going to be extremely useful. They're going to be the things that you're playing with, be able to solve all these problems, man. You're probably going to take statics, dynamics. You're going to need vectors. Vectors are going to need to be your friend. So yeah, I'm going to end this long video. But yeah, I'm excited to teach this. I'm excited for you all to learn this stuff. I'm excited for questions. Man, diving into physics makes you think a lot about the world around you and how everything works, and how makes you question a lot of things. So yeah, I'm excited for those questions. Thank you.